right, thank you guys. So I'm here to tell you a little bit about a case that we ran into while doing our normal business. And that has to do with a really large index that has to be constantly queried all the time and different pitfalls that we found around it, right? So I'm going to start just going by the use case. Just as a little background, this client came with the system already built. Someone already built the index, defined all the mappings, install a cluster in AWS, hosting it in AKEs, so in Kubernetes. It's not in OpenSearch service. And they had the problem that it was really expensive, right? They were having bills, monthly bills from Amazon that were way beyond what they originally expected to be facing, right? So the original engagement with us was simply try to, resize this so we can have a better use of our money and maybe make it a little bit cheaper, right? And from there, we pick up into trying to not only make it cheaper, but make it better, right? So to start by the use case, I'm going to ask you whether you think your personal information is truly safe. And I usually think it is, right? You do all the usual things that you should do to perform safe or to use safely the internet, right? So you do sensible passwords. You don't use 1, 2, 3, 4, and you update those passwords frequently. You also maybe use password managers because right now we have so many passwords that remember them all is almost impossible. So you do safe, secure, responsible password manager to store that. Maybe you even use VPNs and you keep all your antivirus software, whatever you choose to use, up to date always. You take your business classes and mandatory trainings about phishing, so you know not to answer to emails that are fishy. You do all your browsing with HTTPS, and of course, you keep mum on social networks, right? You don't go talking about things that you should not be talking on social networks, right? But even if you do all those things, are you really sure that you are completely safe on your systems, right? So let me tell you, there's a lot of public data out there in what we call the dark web, whatever that is, right? So there's a lot of publicly available software sources, things like government sites that publish anything that it's public domain info. They just put it online on the internet for everyone to use, and they don't really care about it, right? We have company and university sites. They also provide some information maybe about you that you don't know. Of course, the social networks where we volunteer information. And then there's data aggregators and marketing cells, people who just do this for a living. They gather all your data, package it, and sell them around. And then you get to the dark web part, hack databases. And we've heard this from a lot of sites. It happened to PlayStation, it happened to Amazon, it happens to everyone, right? So a lot of your information goes into the dark web in that way, right? Then maybe someday you installed by accident some malware, and then for a few days you were actually publishing some of other information on the internet, right? And then maybe financial activity, right? Some bank makes an error, or maybe there's some public financial information that you need to have, and it simply goes into the internet, and someone collects it, aggregates with some other person's financial information, and then use it for whatever business they have, right? Finally, the credit cards, they have a good history of what we usually do every day. Maybe your bank account. If you are into crypto, maybe you have some sites, some wallets are there, and you can get a lot of personal information for them. So this site or this particular company collects all that data, both from legal sources. Well, they're all legal sources, but both from the normal, like the university pages and LinkedIn and all that stuff, and also scours the dark web looking for things that might have gone there through, let's call them black hat tricks, right? So, as I mentioned, they collect PI information. It's mostly small documents. It's a lot of really simple things of little pieces of information about yourself that leaked into the internet. It's highly structured data. So it's mostly about this is my email, this is my password, etc. And in general, they have over 43 billion records. And that doesn't sound that much given the amount of people online in the world, right? But it does manage. And I assure you that you and every single one of you is in there in that database somewhere, right? So for example, this is a sample of one of our records. That's my email there. That's my personal email that I have since high school, right? And then the password, I cleared that, but that was my password a few years ago, right? So it's there, it's information. And that's just one of the examples for that. For example, that and similar information about myself, it's there at least 87 times. Different times, different years, different passwords as I changed it, and it's there. And I follow all the other things that I said right at the beginning, right? So the information is important. It's there, and you, well, guys, you're there as well. So go home and change your passwords, please. Right? So who uses this company? Mostly corporate security teams, right? Your company wants to know if your passwords have leaked, if one, any of their employees has a security risk, so they hire them and they search on this data for their own domain, their own information, just so they can tell that username, hey, go change your password because it leaked, stuff like that. There's intelligence analysts and law enforcement. Surprisingly, they use it to try to build cases when there's some maybe your identity gets stolen, so they want to build a backtrack of all the things that you have been doing online and maybe your what banking you've been doing. So they go to this repository to get that information, right? And then we get cybercrime consultants, which kind of do the same thing. And what for? Well, to mitigate risk, to prevent and investigate fraud, to uncover leaked person and company intelligence, unmask threat actors. There's also cases where they identify who is leaking information just from going back and mining that information. And then one of the most common litigation support, right? Once things are already in court, they want to go and find some more information about a case. Okay, but that's enough about the actual problem that the database it's trying to solve, which is somewhat interesting, but we're here for the actual index and cluster and the problem that we're having just because of the volume of data that it has, right? So right at the beginning, when we got there, remember the system was already built, right? We had a large data collection built of many small documents, as I already said. It's highly structured, so it doesn't really fit the what we think a search engine is for, right? So far, that it has 87 different type of fields. You see some examples there. License plate numbers, passwords, hash passwords. So not only clear text, social security numbers, passport numbers, etc., etc., etc. Right? In total, there's 43 billion documents. That's 21 terabytes. That's only the main chart, the primary chart. So you have to add replicas to that. And it's growing about 1 terabyte a year as they uncover more data and add it to the collection. One of the biggest problems that this has, and usually when we get and speak to other people about collection this size is, well, how much of it is hot data that you're logging and how much you can move to a colder data storage. But that's not the case for us. They want it all hot all the time, every single time. So every query that comes has to go over all the 21 terabytes of data, got all matching documents and return them to the user, right? So the good news is that they don't expect sub-second performance for those queries. That's at least one thing. We don't have to go back in 20 milliseconds with all the matching data, because the other thing is that they're not looking for 10 or 20 documents, right? They're looking for all the ones that match your user account or the name that you're searching or the address or whatever, right? So 2-3 seconds is perfectly acceptable for them. The index, as it used to be, right, was one single monolithic thing, right? Thank God, thank to the God of search engines, that OpenSearch, or at this time Elasticsearch, has shards, so they at least divide it in 160 shards, so it's not that much of a single monolithic. but it was still 160 shards of data that if you do the math from the data they gave you, it's going to give you about 95 gigs per shard, which is, I'm sure you know, way too big, right? The cluster itself is quite simple. At that time, it was 3 master nodes, and those are going to stay pretty much across the information, and then 17 data nodes with 6 vCPUs, 64 gigs of RAM, and about 1.5 TB of disk storage. Of course, the classic 64 gigs of RAM are divided 32 for the operating system and 32 for OpenSearch or Elasticsearch at the time. And the whole thing is managed in a Kubernetes cluster that is hosted in AKS and EBS storage, AWS storage, right? So what about the queries that are done against the system, right? So the user hits an endpoint in the AWS's endpoint system that triggers a Lambda function that does all authorization, authentication, all the things that you need. And that's the one that goes to Kubernetes to our OpenSearch cluster. Again, at that time, Elasticsearch, now OpenSearch, right? And what types of operations? It's mostly Boolean operations and specific terms and specific fields being queried. So things like that, an email that includes pablo.arce or the username parse, and maybe on that IP range over there, right? It's mostly like that. There are a few fields that are full text search, but those are mostly the ones where when they're parsing the data that they found, they don't know what to do with maybe some information they found, so they add it to what we call an open data field, which is just free-form text for whatever we don't know how to classify it into the other fields, okay? So there's a little bit of full text search, but it's mostly directly to the highly structured data, sorry. Okay, so how about performance? By the time we got there, they had one query every 3 days, right? And at that query level, everything works, of course, right? So the first thing we try to measure is, wait, how this cluster that you have is actually, behaving and performing. So we try to get a simple test, and we say, for about a half an hour, we're gonna try to fire at you at least 20 queries per second. So it goes around, I think, 50 concurrent users at any given moment on your system. And you see that big red line there are failed queries, queries that didn't even answer. They gave a 429 error message back. And then the few that did answer, the little yellow bar there, took at least 1.2 milliseconds. 1.2 milliseconds, of course, being acceptable for the standards, but not returning everything but error, clearly not. So in detail, about 91% of the requests being made ended up as 429 errors. The mean request, total request, was 15 seconds. That is simply affected by the fact that the system has a specific time undefined, right? So since most of your queries are hitting that time and returning an error, you're gonna get around a 50% sec mean. That's it. And the maximum one, the one that took the loss, was 85 seconds. So that was simply not acceptable, right? Kevin does not approve of that performance and that system. So we have to go back and look into our data and what is happening. So we go into the weeds and investigate what's happening, exactly what is going wrong with when we run queries. So the first part was, as I mentioned before, that we needed to make the cluster cheaper, and it was really badly sized. They had more EC2 instances that they needed to run the Kubernetes system. So we started just by fixing that. And we cut a lot of the resources that they have and actually set up something that really, the closest resemblance to what they already have, but in a much more cost performant way. So we ended up with changing from 17 data nodes to 21 data nodes. And we reduced a little bit the size of disk simply because we had more nodes. And then the memory disk ratio improved a little bit, right? The old cluster had 1 gig of memory per every 23 gigs of a disk. The new one is 1 to 21, so it's a little bit better. Both are perfectly within what both OpenSearch and Elasticsearch um, recommend for hot data sets, right? By this time, we also merged took all the system away from the Elasticsearch that they had, which was 7.1, and we moved it all the way to first Elasticsearch 7.10, then OpenSearch 1, and then OpenSearch 1.1 at the time, and I think we're sitting around 1.4 at the moment, right? So from here on onwards, it's all OpenSearch performance, no longer Elasticsearch, right? The other change we made is that we took their big monolithic index and we divided it a lot, right? At the time, we made 9 indices, and right now, I think we're around 11 since we are adding every time more data it's added, right? The new indices are 42 shards each. So if we have 21 data nodes, then there's 2 shards per node plus the replicas. And we have the shards sitting around 40 gigs each, which is what we want. We wanted to take it as close to 40 without reaching the 50%, 50 gigabyte limit that Elasticsearch usually suggests, and I think OpenSearch maintains. But we didn't want to have a small indices or simply dissimilar shards, some really small ones and some really large ones. We wanted to evenly distribute data around the system, right? So just from those 2 changes, we go back and we do another comparison test. So we do the same type of index, right? Same level of load for the cluster, and we get these results. So the error line falls a whole bunch, and that's just a win from that when we from the previous version that we had, right? About 5% were 429 error codes. That is good. It went down. The mean query went to 21 seconds, so that's not good. That increased, but at least we were getting results back instead of error messages. That's a good one, right? And then the maximum went down from 89 seconds to 53 seconds. So in average, they were taking longer, but in total, it was a better performance, and at least people were getting their responses back instead of errors. Okay, so at this point, you're gonna thinking, what's happening there? Yeah, sure. No, it's even simpler. There's a date added for each record, and we use that date. And it's not the date that the data leaked or anything like that. It's simply the date that it was found in whatever source we had, and it was added. And we do that, and we sometimes even redefine index as index rows, and we need to reshard or resize charts and stuff like that. So we could be simply using that one. And then let's see what's happening. When we run these stats, we're seeing things like that. CPU usage, of course, spiked, right? That little spike there is the time where the the test was running. So you can see it clearly spiked a lot. Memory usage stays about the same, around 40% of the available memory, which makes sense since half of the available system memory is actually dedicated to the search engine. And the one more important one is here. How much did the CPU just stay there waiting for the disk to respond, to read stuff, right? The I/O wait time. And that gives us the information that, hey, this is simply a disk problem. We're waiting forever for data to come back from disk. And there's probably a lot of pagination going and information going back and forth between disk and memory. And that's what eating up all performance. So we go and checked, and of course, cache failures in the memory were through the sky. Cache were simply not giving enough performance. Garbage collection was okay in the JVM. You'll see the normal performance where you see the index building up onto the maximum, then you have a garbage collection, and you see that process that happens at a good interval. that you can predict. So we were okay with garbage collection. And for each query, we noticed that about 60% of the time was spent on the fetch of the actual results. And remember that we are trying to get all matching results, not a single page of data. So this sometimes is about 10,000 documents, 20,000 documents that they have to be fetched. And the remaining, like 35, 40%, was doing the actual query itself. Okay. So let's go a little bit into the fields that we have. We have a total of 87 fields, and we have 3 full text search fields. That is fields where we allowed full text and people to search for keywords and stuff like that, like search happens. And the rest are structured data that we will actually look for a matching document, kind of like a database. In fact, exactly like a database. So that gives an information that maybe a search engine is not the best solution for this problem, right? Maybe a database could be doing a better solution. And we are going to address that almost to the end. Then there's the thing about relevancy. And a lot of the process of building a query and executing a query in any search engine is calculating the score for each matching document and ordering it, right? So that the most relevant documents are on top. But we don't care about relevance in this particular case. They just need every single piece of information that it's about the user being searched. And that is truly a game changer, because there's a lot of CPU time, there's a lot of effort being used into calculating that. But more importantly, there's a lot of data being stored about each token, where does it appear, how many times does it appear. There's a lot of calculation being there that is used simply for calculating a value that we are not using and we don't care to use. So we went back and we changed all the field settings that we had, right? Since we don't need scoring, we can disable norms and we can do the index option docs, right? So that way we are not storing any information about how many times a document appears in a particular document or how many times it appears across the whole corpus of information. We do not need to do big sorts of aggregations. So we can disable doc values, and that's a whole bunch of information. Our index decreased about 15% just by those 3 changes. And since the name of the game here is disk and disk throughput, this had a good impact on performance. The question that you might now have is, what are you running this thing on, right? What type of disk is this running on? So the original one and all the results that you've seen so far, it's on EBS GP2 volumes that at the moment were the standard, right? They use around, it depends on the size of the EBS volume that you request for, the amount of IOPS that you're gonna get and the max throughput that you're gonna get. But at the size that we were requesting, we calculated that we were around 3,000 IOPS per second and around 200 megabytes per second, right? So one of the things now that we wanted to change was simply move to GP3, which at that time were just brand new coming out, and you can actually request to have more information. So we doubled those values that GP2 were giving us, right? Then there was also a final change in the cluster structure, and that was simply due to some changes where we moved to a cheaper instance on the Kubernetes service, that we had to move the shards around. This had nothing to do with the performance of the queries. It was simply about the Kubernetes stuff, but it ended up helping us a lot. So from this that we had before, we moved to this solution where the same number of master nodes, those don't change ever. We kept the 21 data nodes that we reduced from 64 gigs to 50 gigs each. So that was done simply so we can put, before we could host 3 data nodes inside each Kubernetes node. Now we can fit 4 of them, right? So we actually, after doing all this process, we could have one less EC2 instance running. And we added those ingest nodes. And that is because ingestion is almost constant. It happens mostly at night when there's lower queries happening. But there is some transformation there that take away some of the CPU. And we were noticing that they interfere with queries. So we wanted to restrict them to their own set of data nodes and have them only them do ingest. And when they're not ingestion, they're also working as data nodes and answering queries the same as everyone, right? And through all these changes, all the ones that I described before, the changes to remove the information that had to do with scoring that we didn't need, the changes through disk to have more throughput and more IOPS per second, and then these changes on the cluster topology, we got much, much better results. Completely day and night from what they originally were sitting, right? Now we are sitting at 0% for 29s. We don't get error messages for no users, at least at this level. Again, I repeat, it's 25 users coming in every second. We get sub-second response a few times, under 800 milliseconds. The average or the mean query takes a little bit less than a second. For most search engines, this is incredibly slow. For us, it's actually well within the 3 seconds that the user requested. And then the maximum, when it's really loaded, is taking 15 seconds, which is still not what we want, but at least it's lower than what we had before, right? So we've done it, Kevin. We fixed the problem a little bit. We need to keep working on that. And now through this performance, what about cost? Well, we have half the cost as well of the original cluster. So they had a cluster that was simply not able to handle 2 users at the same time. Now they have one that you can have at least 25, 50 users at the same time at half the cost through a lot of incremental changes to checking and monitoring everything about how OpenSearch works and trying to do the best optimization possible. So next, are we done? No. First, we're asking to move to IO2 volumes. Those are clearly more faster than GP3. I told you before that before the optimizations, we were like 60% in the fetch execution, on the fetch part of the query, and the rest on the actual query and querying the indexes and calculating the starts. Now we're sitting about almost 90% of the query time goes just through fetch. So it's our biggest bottleneck by far. So what can we do to fetch faster, but throw hardware at it? There's no much solution that we can. So we are moving from EBS to IO2 and hopefully SSDs. The other one is that since we are moving to IO2, we might as well go away from AKS and simply do the managed version from AWS OpenSearch, right? No reason for that. Our cost will go up a little bit, but I don't think it's gonna be nowhere near what we originally were paying for the cluster. So it's still gonna be price performant, right? And finally, DBs. We did try a little bit with several databases and some other non-search engine solutions, because remember, a lot of our data is highly structured. So if you have a highly structured data, why use a search engine by itself, right? Now, there's a caveat here. We only did small-scale testing. We did a subset of the documents. We tried to make it as representable of the whole collection that we have, but still, it's a much, much smaller scale, so we can run tests without breaking the bank, right? We tried Postgre, a simple SQL solution. We chose that one. I don't know why. We like Postgre more than MySQL for some reason. We just wanted to test, right? But we know that wasn't gonna work pretty much because we're missing the full text data search. And it's not that much used, but the users that do use it really like it. So, a pure SQL system is just not gonna cut it, right? Then we did some experimentation, trying to do a Cassandra Solr combination, right? This was highly experimental. I know there's an Alessandra thing that kind of does it already out of the box, but it requires a lot of development. They already have developed Elasticsearch / OpenSearch solution. They don't want to change that much in their approach. And that was discarded just from the amount of work that we will need to put this into a production ready environment. And so the cost for that one is estimated to be similar. So there's no real point of going, if you're gonna have to spend a lot of time and effort to get it to production, and it's gonna cost about the same, why do it, right? And then we went to a NoSQL database that has a Lucene-based search component. I'm not gonna name it, but probably you know which one it is. And here we got a better performance than the cluster that we saw, for sure, right? When we were doing queries just for fields, like give me every field where the user is Pablo, then we got much faster responses. And then the full text queries that are rarer work well with this Lucene component that the database asked. The problem there is that we tried a lot, but we cannot even come close to the cost, not even the old cost of the original cluster. We're talking about 4, 5, 6 times the cost of our little Kubernetes cluster, simply because of the storage costs. Okay, so that was at that end from that point. Maybe at some point we're gonna find some other solution that works well. I'm not a fan of using the wrong tool for a specific solution, right? If you have nails, you better be using a hammer. If you have screws, you better be using a screwdriver. And right now, through this process, I keep thinking that I'm using a hammer to hammer screws into a piece of wood. But it's working. It's working and it's performant and it is more cost effective. So there's value in that by itself, right? There's some few lessons that we learned just to summarize. Follow guidelines, right? The single index with these huge shards. Everyone will tell you that's not a good practice. I think you all knew when I told 93 gigs per shard that you all saw that, well, that's wrong. So just follow that. Guidelines on index topology, on shard size, on memory ratios. Keep them up and just check that you're following that. Experiment with different configurations. That has been a lot of problems. There were surprises when we did the last change to the topology where we reduce the memory available to each node. I thought we will have a performance hit, and it was the other way around. We got a little performance improvement just from reducing the amount of memory available to each node, but increasing the number of nodes. So that was a surprise. Experimentation always pays off, even if you just validate what you think is going to happen. Find your bottlenecks and attack them. Right? We are sure right now that our bottleneck is disk and disk throughput. Right? So the only way we have to attack it is get faster disk, but we're gonna do just that. And then always keep an eye on performance cost, because that's what our clients want, right? At the end of the day, the best possible solution at a lower cost. And that's it for this case study. So thank you very much.